Hello guys, this is Prime Concept. I want to continue with the concept of electric dipole. In our previous video, we explained this, we introduced it and did some derivations. Now, one of the things we established is that electric dipole is denoted by the symbol P. An electric dipole has a relationship which is P equals QD. Now, what is an electric dipole? Just a reminder. An electric dipole is a pair of positive and negative charge with equal magnitude separated by a distance d. So that is an electric dipole. Now, one of the things we'll be mentioning here is that electric dipole is a vector quantity. So this is a common problem you would meet in exam, very simple. So electric dipole, you should know, is a vector quantity. That is one thing you should know. Then another thing we want to establish is the unit for electric dipole. So it is a vector quantity. So the second thing we want to establish is the unit. Now, you notice that Q is charge and Q is measured in coulomb. So you have coulomb, then D is distance, which is in meters. So you have coulometers. Coulometer is the unit for electric dipole, right? Now, if we have a dipole placed in an electric field, we want to bring out something, deduce some things. You have a dipole placed in an electric field. Say this is positive and this is negative. Of course, we established that the distance of separation is d. Now, what is the direction? Since electric dipole is a vector quantity, what is the direction of the electric dipole moment? Electric dipole moment would always point from the negative charge to the positive charge. So it would act along the line that joins them. So it will point from positive to negative. So this is going to be the direction. This is going to be the direction of the electric dipole P. It's always going to point from this to this point, right? Now, if we place this dipole in an electric field and the field has a direction like this, this is the field direction. So at what point do we get a stable dipole? Remember I told you in my previous video that when you place a dipole in an electric field, that dipole would experience a tug, right? And I mentioned that that tug acts to reduce or to stabilize that dipole, to reduce the angle between the dipole and the electric field. This is the angle between the dipole and the electric field. So the tug always acts so that it can minimize this angle, right? Now, when it does that, it eventually brings the dipole to a stable equilibrium position. And what is the stable equilibrium position a dipole can attain? A dipole can attain a stable equilibrium position when the angle theta is equal to 0. So when the angle theta is 0, the dipole attains a stable equilibrium position because it will now become parallel to the electric field. Now, it can also attain an unstable equilibrium position. So a dipole would attain an unstable equilibrium position when that angle theta is equal to 180 degrees. That is to say, the dipole is now anti-parallel to the electric field. See, the electric field is pointing forward, the dipole will be pointing backward. So these points are worthy of note. Now, we also established the formula for the net force on the dipole. We mentioned that the net force on a dipole is going to be 0, it's always going to be 0. And the reason is very clear, right? Now, another thing we mentioned is the formula for tug on a dipole. The tug, we said, is PE sine theta. That is the tug, right? And then we also established, of course, you should know from this that you would get maximum tug, the highest tug, when theta is what? When theta is 90 degrees, so you get your maximum tug. Now, we also established the formula for potential energy. Potential energy, we said, is U equals minus PE cos theta. Now, some persons may get it wrong here. Now, if you are asked, when do you get the maximum potential energy? The maximum potential energy is attained. Maximum potential energy is attained when theta is equal to 180 degrees. This is when you get your highest potential energy, right? And then the minimum potential energy, the lowest potential energy you get is when theta is equal to 0. That is to say, you get maximum potential energy at the unstable equilibrium position. Then you get minimum potential energy at the stable equilibrium position. So do well to note this point. So I want to solve one simple example in this video that will illustrate this concept. Let me put the question on the board. So we have our problem on the board. The question says an electric dipole of dipole moment this. So it means we have P, which is 4 times 10 to the power minus 9 coulometer, that is the unit, is placed in a uniform electric field of this. That is to say, the electric field intensity E is 5 times 10 to the power minus 4 Newton per coulomb, making an angle of 30 degrees with the direction of the field, right? So the angle theta it makes is 30 degrees with the field. So that means the torque exerted by the electric field. So we're looking for torque, we're trying to find torque. So the torque is going to be this, which is equal to PE sine theta. And our torque is going to be 4 times 10 to the power minus 9, 5 times 10 to the power minus 4 sine 30 degrees. So if I punch this, I would have 20. Okay, 4 times 5 is 20, sine 30 is half, 20 is 10. So I have 10 times 10 to the power 9, okay, this 10, 13. So minus 13 Newton meter, that is the unit of torque, Newton meter. So this is the torque for the question. So I would leave you to solve. If the question goes further to ask for potential energy, what would the answer be? Solve it and drop the answer in the comment section. Let me give you hints. For the potential energy, you will be solving U equals minus PE cos theta. So you can find the potential energy with this. So do this and drop the answer in the comment section. Thanks for watching. I believe this concept is very clear. Do subscribe to my channel, like my videos, and share with your friends so that they can also benefit. Remember, this is Prime Concept. Thank you.